Hello again, this is Michael Creutz. This is the beginning of the third lecture in my series of Introduction to Lattice Gauge Theory for the INT Summer School in 2021. I should mention that all of these lectures, the slides are available, so if you want to go back and explore some of the finer points, you don't have to slog through the long video file, you can just go through the slide file. Okay, so today's talk is going to be about some of the peculiarities of trying to put fermions on the lattice. And again, it's not going to be about Monte Carlo, it's going to be about just the basic formulations. So let me go back to my slides. There they are. Okay, so I'm going to start with a very simple argument that has to be a little bit complicated with lattice fermions. So let's imagine some lattice Dirac operator. Now normally in the continuum we have a Dirac operator which has a kinetic part and a mass part. So let's try and do that for a general Dirac operator. So I'm going to assume that there's a gamma 5 hermiticity floating around, that gamma 5, d gamma 5 is d dagger. And this is true in most cases. It's not quite true with the twisted mass things, but it's effectively true for all of them. So let's divide whatever this operator is into two parts. One should represent the kinetic part, and one should represent the mass. The kinetic part is going to be the anti-Hermitian part, and the mass piece is the Hermitian part. So if we do this, by construction, the kinetic part anti-commutes with gamma 5, and the mass term commutes with gamma 5. Now on the lattice, everything is finite. So trace gamma 5 indeed vanishes, unlike what I told you for the continuum yesterday. This means that if I take my mass and multiply it times the phase, this is an exact symmetry of the fermion determinant. K plus m, I just put my gamma 5 theta over 2 on the left and on the same thing on the right. These cancel out on the kinetic term, but they put a phase into the mass. And as I told you yesterday, a phase in the mass is related to the theta parameter. So where did the anomaly hide? This must be a Flavor-Carroll symmetry. It's the only way it can work. All lattice actions must bring in some extra structure. Now, naive and staggered fermions do this by having doublers. Half of them using gamma 5 and half using minus gamma 5. So you have this wrapping I talked about before. One way around some of them, one way around the others. Wilson does it another way, and overlap fermions also, where the mass term is not a constant, unlike in the continuum. And in the mass term there are heavy states which cancel the anomaly. So if we compare this with the continuum theory is just d slash plus m, which in momentum space is ip slash plus m. This is what we want to mimic on the lattice. And here d has both Hermitian and anti-Hermitian parts. The Hermitian part is the mass, and the anti-Hermitian part is the momentum. And in the continuum theory, the Hermitian mass term is a constant. This will not be the case on the lattice. The lattice, when you put a field on a lattice, it replaces the continuous momentum with trigonometric functions. So the lattice transformation involves replacing, when I go from the position space to the momentum space, I sum over all. We do a Fourier transform with discrete momenta. And to do the reverse, you integrate over the q's. I mean, actually the q's are not discrete, but lattice variables are, and you go back. Now for naive lattice fermions, we replace the derivative with nearest neighbor differences. Nearest neighbor differences gives you signs. So p slash plus m psi becomes psi bar I over the lattice spacing, gamma mu, sine of the momentum, plus m. And this at very small momentum, when p is very small, goes to exactly the desired thing, p slash plus m. But the sine function has other zeros in it, and the one at 0, there's another one at pi. So whenever p mu is any component of p mu is pi over a, you have another place with low energy excitations. So instead of the one naive fermion, we have 2 to the 16, a factor of 2 from each dimension, or 16 doublers, 2 to the 4th. Now, Wilson solved this problem very early in the game by saying, okay, let's just make the mass depend on the momentum. So we still get this sign factors we had for the kinetic part, and we got our mass, and he adds something, 1 minus cosine p mu a, times some parameter r, which is just somewhat arbitrary. And so when the momentum is small, 0, this just cancels the 1. So the r over a is of order of the lattice spacing goes away. But when you get out to order of pi, these don't cancel anymore, and you get the eigenvalues pushed up to something of order 1 over a. Okay, so let's proceed. So it's easy to diagonalize the free Wilson theory. The eigenvalues occur, well, there's the I erase sine squared stuff, which you have from the continuum. And then you add this correction, and so when the momentum is large, you get an addition to the momentum. Both the real and the imaginary parts are even at m equals 0. Oh, I'm sorry. There are both real and imaginary parts, even when the mass vanishes. Okay, the eigenvalues, which is different than the continuum where the eigenvalues are always imaginary when there's no mass. You can plot this out. They form what looks like a set of nested circles. Here's where m is where the massless particle, where the particle occurs. But then there's all these funny circles, and these are the imaginary part of the eigenvalues and the real parts. Now there's something to observe about this. One, several things. First of all, m and going to minus m is no longer a symmetry. But we learned in the other lecture that this is essential for QCD with an odd number of flavors. Chiral symmetry is broken because this extra term does not anticommute with the gamma 5. Because there's no chiral symmetry, the mass can in fact get an additive renormalization, and in fact does. Okay, so what I talked about at the very beginning was essentially the Nielsen anemia theorem, and I'm going to try and describe it a little more formally now. This doubling issue is closely tied to topology in momentum space. So let's take a particular gamma matrix convention to make this clear. I can take my gamma vectors to be sigmas in the off diagonal. I can take gamma 0 to be i's in the off diagonal. And I think I've got an unconventional, there should be a sign here somewhere. Anyway, gamma 5 is the usual thing, 1 and minus 1. So now let's suppose a Dirac operator anticommutes with gamma 5, which is what we want, which anticommutes here. Oh, there's something wrong here. I need to fix it. In momentum space, the Dirac operator is a 4x4 matrix function of the momenta, which has to anticommute with gamma 5 now. And so the most general form of a matrix which anticommutes with gamma 5 is an off-diagonal matrix with two terms in here. These must take the form of z0, some constant, plus I sigma vector times a 3 vector. And any chirally symmetric Dirac operator must take this form, which means it maps momentum space into the Quaternions. These are called Quaternions. The massless Dirac equation expands the Dirac operator around a 0, so we want d of p to be p slash at some point, like gamma mu p mu. So let's consider a sphere of constant magnitude of p surrounding one of these zeros. these quaternions on the surface of this sphere will wrap non-trivially around the origin. Now, the momentum space must have Z of P be periodic. That's the thing about the lattice, that everything is periodic in 2 pi. So any place which wraps around a 0 here must unwrap around another 0 somewhere. When I do the naive fermions, they divide into 2 groups of 8 with opposite mappings. Half of them will go one way and half go the other way. So the conclusion here is any chiral lattice gauge theory where D anti-commutes with gamma 5 requires an even number of massless species. So that was the theorem I talked about at the beginning. Now, there do exist actions with just 2 doublers. They're known. They should be pretty good for simulations. They do keep the multiplicative mass renormalization, which is a nice feature. But they haven't been much used yet, so they maybe get more use with time. The known variations all break hypercubic symmetry in some way or another. And this introduces counter terms associated with the hypercubic symmetry. The point is that the direction between the 2 zeros picks an axis. And this broken hypercubic symmetry can renormalize the temporal hopping, can also renormalize time-like plaquettes. But it is an amusing thing that a single field can create 2 different species. Okay, let me go on now to talk about another very popular approach, the domain wall and the overlap fermions. Now, Wilson fermions, it turns out, if you take the mass negative, can have surface modes. You can have modes on the surface of your crystal. These modes are naturally chiral, and they can only mix through the tunneling between the 2 surfaces. This really is an example of what is very popular in condensed matter physics these days of a topological insulator, where you have robust conductivity only on the surfaces. So the idea of domain wall fermions is to use this. We work on a 5-dimensional lattice of a finite 5th dimension and identify the surfaces of this 5th-dimensional lattice as our 4-dimensional world. And so our world lines exist on one wall, and on the other wall there's the parity partner list one. If we're right-handed up here, there'll be a left-handed partner list down here. And then you can try to make the bulk modes go to infinity in the continuum limit. So that's the idea of domain wall fermions. The overlap is basically a limit of that theory. You drive the bulk modes to a very large energy. You take the size of the 5th dimension to be very large. And it's called overlap because you can think of it as being an overlap of 5-dimensional transfer matrices. Effectively, it's a 5-dimensional transfer matrix between Wilson fermions with positive mass and Wilson fermions with negative mass. Now, this can be formulated directly in the 4 dimensions. This is something Neuberger showed quite early. So let's require that our Dirac operator gamma 5 go through it and give the dagger of it, which is common in most actions. And let's replace the anti-commuting of D with gamma 5 by anti-commuting with an extra term. This extra term allows us to define what is called gamma 5. D on gamma 5 is gamma 5 hat on D. This relationship here is called the Ginzburg-Wilson relation. It is just like the naive anti-commutation, but it has an order A correction. It's you can work this out for yourself. It's equivalent to the unitarity of a certain combination. 1 plus the lattice spacing times D has to be a unitary matrix. Ginzburg-Wilson relation can be rewritten by saying V dagger V is 1. Very simple way to write it. Neuberger suggested we construct this unitary matrix by a unitarization of some other Dirac operator. So he said start with an undoubled Dirac operator, something like the Wilson one, and project it onto a unitary matrix. And I misspelled unitary, of course. So we're going to take V and write it as the Wilson operator times dw dagger to the minus a half. So what does minus a half mean? Well, it means, first of all, you diagonalize d dagger d, take the square root of all the eigenvalues, and undo the unitary matrix which diagonalizes this. Effectively, you're taking this Wilson operator. First of all, it's got negative mass to get the surface modes, and projecting this onto a circle. And that's the overlap operator. So given this V, the overlap operator is just 1 minus V over A. Now this has a lot of interesting properties. First, well, of course, the first one, it's very computationally demanding because you have to do that inversion of dWd. It has a nice property, though, that the Wilson operator, because it's constructed from a unitary operator, in fact, it's a normal matrix. It commutes with its dagger. This is not true for Wilson, which is a nice exercise for you to show yourself. It does satisfy gamma 5 d, gamma 5 d dagger, but the chiral symmetry is somewhat modified. If I take psi and multiply it times some angle times gamma 5, I have to take the psi bar and multiply it times a different gamma 5. And this different gamma 5 brings in this factor of V. Now, as with gamma 5 dagger is Hermitian and squares to 1. So all the eigenvalues are plus or minus 1. And from this operator, you can define an index. You can take the trace of it. It's not, gamma 5 is traceless because it's just a 4 by 4 thing. But this thing is not traceless, and this is a way to get your index. It has new exact 0 eigenvalues, and this definition of new agrees with the continuum index if your fields are smooth. The half here is coming about from real modes on the opposite side of the unitarity circle. There are some issues with this approach. It is somewhat arbitrary what operator you start with. I mean, the Wilson operator is just one possibility. But even with the Wilson operator, there's a dependence on the hopping parameter. You do need to keep the mass negative so that one species projects out. But you also need to keep the mass not too negative because the doublers come in. So this is easy to illustrate. If you try to project these eigenvalues onto a circle when you have a positive mass, well, you're not going to get any down near the origin. Those are the massless particles you want. So you still satisfy the Ginzburg-Wilson relation, but you don't have any massless particles. On the other hand, if you make M2 negative so that you're in the second unitarity circle, and second of these nested circles, you will project not only the original massless particle you want, but the 4 doublers, lowest doublers. And so you actually have 5 quirks in this approach. So Ginzburg-Wilson relation does not require massless Goldstone bosons, nor does it tell you exactly how many you've got. The winding number can depend on the choice of the mass, how negative the mass is. This can depend on eigenvalues inside that first circle. Once you turn on the gauge fields, the eigenvalues leave those nested circles. Another interesting question is how local is it? Because you're inverting this matrix, it is no longer a sparse matrix. And it has been conjectured that the non-locality is exponentially suppressed at long distances. This I don't believe has ever actually been proven, but it seems like it might be true. An interesting issue is the one-flavor theory, which I talked about the other day. The one-flavor theory doesn't have any kind of jump in the condensated vanishing mass, which means somehow this projection onto the circle must leave a gap in the eigenvalue spectrum at 0. This has not really been studied. I think it would be an interesting problem. It's also been shown that when the fermions are not in the fundamental representation, the counting of numbers as zeros can get screwed up on rough configurations. This was shown some years ago. Okay, so let's come to another formulation of fermions on the lattice, the staggered fermion formulation. This is actually quite a fascinating formulation because you start off with fields that don't have any spin. You don't have any spin a half. And yet, when you get done with the formulation, you discover that spin a half particles are there. This is a amazing thing where spin kind of emerges from the formulation. So I'm going to give one derivation. There's many derivations of staggered fermions. This is one I kind of like. Let's start with the Z2 field on a 4D lattice. So we're going to have every link be plus or minus 1. This is not the fermions. The fermions come later. And we're going to take this Z2 field and drive every plaquette to minus 1. Effectively, if I had a beta for the Z2, I'm taking it to minus infinity. So if every plaquette is minus 1, it's kind of like having a half integer of magnetic flux through every plaquette, because whenever a particle runs around that plaquette, it gets a minus sign. Oops. Here's a particular choice, which is rather convenient, so I'll stick with it for now. If I set all the x links to 1, the y links to minus 1 to the x coordinate, the z links to minus 1 to the x plus y, and the t links to minus 1 to the x plus y plus z. This will actually make all the plaquettes be minus 1. So here's a two-dimensional example. You put some links to minus 1, some are 1, and it's set up here so that every plaquette has minus 1 when you go around it. Now this messes up translation invariance. The translation in the z direction here is by 1 unit, which is the normal thing. But in the x, y, and z directions, I have to go 2 steps to get back where I started. So the basic unit cell actually has 8 sites. It should just be 2 in the two-dimensional example here. This unit cell is 2 sites. These 2 sites here. Now, once you've got these phases put on the links, now we put a spinless fermion field on this lattice. So it's got no Dirac algebra associated with it at all. The fermion still has color indices and flavor indices, but no spin indices. And the eigenvalues of this spinless field on there are just the usual result for a free particle hopping on the lattice. So the sum of the, I've done it with cosines. You can do it with sines if you want. It doesn't really matter. So you get the usual, what looks like the usual doubling. But because the translation symmetry is by 2 in the spatial dimensions, components of spatial momenta are actually only in half zones. They go from 0 and pi, not from minus pi to pi. The temporal momentum still has the full zone because that is has a translation of 1. So what you lose all the doublers from the spatial direction, but you keep the one in the time direction. So we can interpret this 8-site unit cell as 2 4-component spinners, and each of these 4-component spinners has 2 zeros in momentum space. They're all the plus pi over 2 in the space directions and plus or minus pi over 2 in the temporal direction. Effectively, you have 4 independent Dirac species. These are usually called tastes these days to distinguish them from flavors. Now this theory has a chiral symmetry, an exact chiral symmetry. Since it only involves nearest neighbor hopping, the action will anti-commute with putting a -1 to the parity of the site on each side. This plays the role of gamma 5. There are 2 Dirac cones for each chirality, and you wind up with a 4-flavor theory with 1 exact chiral symmetry. Now, as I said before, it actually has to be a flavored chiral symmetry. these are staggered fermions. Spin is emerging dynamically for a one-component field. The Z2 background field at beta equals minus infinity gives you a whole bunch of crazy sign factors on the links, but it inherently has multiple degenerate species, and multiple degenerate species is required for chiral symmetry. Now, it's often assumed that this taste symmetry becomes an exact SU4 in the continuum. So if we do that, you can think a little bit about the spectrum of states. And it's a little bit complicated, because SU4, if you take, let's look at the neutrals. So let's take a U bar U state. The U bar U is a 4, and the U bar is a 4 bar. And when you take the group SU4, this gives you a 15-plet and a singlet. So you get 15 UU bar states, 15 DD bar states, but these actually cannot mix with each other because they are independent taste groups. There's one for the U's and one for the D's. But the singlets can mix. You get one singlet from each of the U bar U and one singlet from the D bar D. And the singlets combine in the usual way to form the singlet pi naught and the eta. But we have three distinct neutral meson masses. And if the isospin is broken, if the two quarks have different masses, there's actually 4. This is one for the U bar U, one for the D bar D, and then 2 masses for the 2 singlets that can mix. Now, the singlets have different decays than these things too, because they have different taste structure. In the physical theory, this is different than in the physical theory, where there's only one pi naught and one eta. You can give exactly the same argument for the vectors. The rho and the omega are not degenerate with each other because they are have different symmetries. All right, so now I'm going to jump on to something called twisted mass. I'll do this very briefly, so you guys that are interested in it can go play with it. For the continuum theory, for the 2 flavors, there is this exact flavored chiral symmetry. You can multiply psi by e to the I theta gamma 5 tau 3, which is what mixes the sigma and the pi we talked about before. This makes it interesting to think about a generalization of the mass term. Let's do this kind of rotation to the mass term. Mass would give a mixture of a psi bar psi piece and a psi bar gamma 5 tau 3 psi piece. But since this is a symmetry, and a valid symmetry, for the 2 flavor theory, we get the equivalent theory with the mass, which is just the sum of the square root of the sum of the squares of these 2 parameters. Now, what's interesting about this is that the lattice artifacts break this symmetry. Something like Wilson fermions do not keep this symmetry. And with degenerate Wilson fermions, Aoki talked about this a long time ago, they can in fact generate all kinds of weird little violations. You can get a spontaneous CP violation, you can get a flavor violation, and this can occur over a finite range of hopping parameters. Hopping parameters are the mass parameters. And in this flavor violating region, you get 2 Goldstone bosons from the flavor breaking, and then you get a 3rd massless state at a 2nd order boundary when you enter this funny phase. And Aoki argued that when you take the continuum limit, these 2 combine with this to give you the pions. So this coefficient of psi bar gamma 5 tau 3 psi is kind of like a magnetic field conjugate to this Aoki phase. So if I look at, here's the mu axis, here's the ordinary mass axis, and there's this funny phase where Aoki says this business can happen. So the argument for twisted mass is to go off into this, turn on some mu, and go up here directly above this. And the idea is that then the order A lattice effects can be tuned to cancel. They change sign as you go across this thing here. And the other main motivation is this is much faster than overlap or domain wall, so you can tune away a lot of the artifacts. Now there's still some tuning necessary because you have to know where this point is to get up here, but once you've got that figured out, you've got a very nice action for simulating. Okay, so I've gone all through all this stuff very fast, and so I'm sure you've all lost, but you'll be learning a lot about it from other lectures at school. Staggered is very, very fast, which is why it is very popular. But the spectrum is not really QCD. It's got some weird issues with it. The Wilson theory is very fast, but chiral symmetry is pretty nastily broken, and if you're relying on chiral symmetry to help you in your calculations, can be difficult. The minimal doubling, it needs more study. Counterterms are needed, and we'll see where they go. The twisted mass is very fast. It needs a little bit of tuning to get to the critical point where the errors cancel. Domain wall has an improved chiral symmetry, but at a cost of having this extra dimension and more fields to play with. The overlap is rather slow. However, it has extremely elegant chiral properties, and computers have become very, very fast. And it's being used more and more. Which is best? Oh, I don't know. All of them allow various improvements. You can do some smearing, etc. All are in current use. You have to pick your favorite. And the details of the numerical algorithms will be covered by the other lecturers. I think that's it. So, thank you all for, let's go back to my picture. Thank you all for listening, and this was a bit scrambled, I know, but we can go back through it many times and hopefully get something out of it. Now I do